Back in your geometry class, you probably saw quite a few different formulas for finding the area of a triangle. I'd like to come up with one that kind of plays off of our new coordinate system idea, right? One where all I need to know are the coordinates of the vertices, and put those into my formula, and out comes the area. Okay, so one way we could do that is to use the distance formula. We could find the lengths of all three sides, substitute those numbers into Heron's formula, and we'd get an answer. It's going to be a messy answer. There's probably going to be square roots in those distances. So your answer is going to have square roots of square roots and sums. It's just going to be a mess, right? There's a better way to do this. What I'm going to start off with is I'm going to drop perpendiculars from each of the vertices down to the x-axis. Right, and I want you to look at what this does. This makes three trapezoids. There's this one here. There's this one here. And then there's this one down here that doesn't actually contain any part of the triangle that we're interested in. We have a formula for the area of a trapezoid, right? It's 1/2 the height times the sum of the bases. So what I'm going to do is I'm just going to apply a really classic geometry technique. I'm going to find the areas of the first two trapezoids that I did, the two blue ones, add them together, subtract the area of the bottom one. And that should leave me with the area of the triangle. Now, before we do that, let me fill in some distances here. This distance, this is the height of one of the trapezoids, is x2 minus x1. This other height, the height of the right-hand trapezoid, is x3 minus x2. And the height of this big one down here is x3 minus x1. And the bases are easy. y1, y2, y3. All right, so what are our areas then? The area of the ABED trapezoid is 1/2 x2 minus x1 times y1 plus y2. The area of the BEFC trapezoid is 1/2 x3 minus x2 times y3 plus y2. Then I'm going to subtract out the area of the bottom one. So that's minus 1/2 x3 minus x1 times y1 plus y3. Now, so far that's not a very pretty formula, right? But there's a lot of cleanup you can do here. I start by factoring out the 1/2, then multiply out all of these polynomial parts. And if you do that, you're going to get a whole lot of cancellation that happens. Now, I'm not going to expect you to sit here and watch me go through some really just very tedious algebra calculations. You're welcome to walk through the steps yourself and see what cancellation happens. But if you do that, you're going to end up with 1/2 x1 y2 minus y3 minus y1 x2 minus x3 plus x2 y3 minus x3 y2. Now, you could very reasonably look at this and say that's not a very nice formula either, and you'd be absolutely right. But if you're familiar with it, with a little linear algebra, just the process for finding the determinant of a matrix, we actually can rewrite this in a very nice form, right? We can rearrange it so that it's just 1/2 this determinant. You notice how nicely the coordinates are arranged. x1, y1, 1, x2, y2, 1, x3, y3, 1. Very quick, very simple formula, easy to remember, I think. One caveat here that you need to keep in mind. For this formula to work, you have to take the vertices in the clockwise order that I took them. Right? If you take them counterclockwise, well, I'll let you figure that out, right? Just try it, right? Try doing it both ways. We'll actually do an example of this in another lecture here. Try doing it both ways and just see what the difference is. So if you want to see some examples of how this formula gets applied, you can click on the upper link here in the upper right-hand corner, Or you can go ahead to the next lecture where we're going to revisit the idea of the slope of a line. And we're going to see how we can connect the slope formula that you learned back in your algebra classes to the angle of inclination that's formed by the line.